What happens when a high-speed stream of solar wind slams into Earth's magnetosphere, sparking a G1 geomagnetic storm, right while an asteroid makes a close flyby and human forecasters fiercely disagree with AI models about what the Sun will do next? Today, we are breaking down everything from the physics of cislunar space to debriefing cosmic claims and tracking space weather in real time. You're listening to the Daily Space Podcast by Flareant, your daily conversation about space weather, solar activity, and cosmic events. I'm Ollie, and today is Wednesday, August 19th. Let's get into what the Sun is doing today. Right, so let's start with our live space weather report. If you've been checking your Aurora apps over the last 24 hours, you might have noticed a sudden bit of action on the charts. Over the past day, our planetary KP index hit a peak of 5.0. Now, what does a KP of 5 actually mean for us down here on the surface? Well, on the space weather scale, a KP index of 5 represents a minor geomagnetic storm, officially categorized as a G1 storm. It means our planet's magnetic field experienced a significant disturbance as high-energy particles from the solar wind compressed and rattled Earth's magnetosphere. Looking at the finer high-resolution data from GFZ Potsdam, the HP30 index, which measures geomagnetic activity in 30-minute intervals, actually spiked up to 5.33. That shows us that the geomagnetic activity came in intense, rapid bursts rather than a slow, gradual build-up. At the same time, our Disturbed Storm Time Index, or DST, dropped down to negative 44 nanoteslas. Why is the DST index so critical to keep an eye on? Think of DST as a planetary thermometer for Earth's equatorial ring current. When solar particles get trapped in Earth's magnetic field, they flow around the equator in a massive electric current. A negative DST value means this ring current is squeezing Earth's magnetic field downwards. A value of negative 44 nanoteslas confirms that we had a solid, moderate injection of energy into the ring current, sufficient to drive auroral ovals much further equatorward than usual. As of right now, things have settled back down somewhat. The latest KP reading sits around 2.67, which indicates unsettled to quiet conditions. So if you missed the bright lights overnight, the immediate peak of this particular geomagnetic event has passed, though elevated solar wind speeds are still maintaining mild background turbulence. It is always fascinating to see how quickly the space environment can shift from tranquil background conditions to active G1 storm levels in just a matter of hours. Now, let's pivot to our deep dive blog articles for today. We have a fantastic lineup of pieces published over at flaint.com that explore the mechanics of near-Earth space, technological impacts, and astronomical phenomena. First up, we have an insightful piece titled "Cislunar Space Represents the New Frontier for Human Activity." When we talk about space exploration, most people automatically picture low Earth orbit, where the International Space Station flies at about 408 kilometers, or they think of deep space missions to Mars. But cislunar space is that vast gravitational playground sitting between Earth and the Moon, roughly 384,000 kilometers across. The article highlights how cislunar space is rapidly evolving from a purely scientific realm into an economic and logistical transit corridor. What makes cislunar orbital mechanics so fascinating are the Earth-Moon Lagrange points, specifically L1 and L2. At these locations, the gravitational pull of Earth and the Moon balance out perfectly with the centrifugal force of an orbiting object. This creates positions of relative equilibrium where spacecraft can maintain position with minimal fuel expenditure. However, operating in cislunar space comes with serious radiation challenges. Beyond Earth's protective magnetosphere, hardware and crew are exposed to full galactic cosmic rays and unfiltered solar particle events. Understanding this environment is crucial as space agencies and commercial entities prepare for permanent lunar infrastructure. Our second article addresses a common point of confusion: the reality of solar flares and global radio communications. Have you ever seen sensational headlines claiming a single solar flare is going to wipe out every cell phone tower and power grid on Earth overnight? Well, this article thoroughly debunks those exaggerated fears while carefully explaining the genuine physical risks. A solar flare is an intense burst of electromagnetic radiation, primarily X-rays and extreme ultraviolet light. Because light travels at roughly 300,000 kilometers per second, solar flare energy reaches Earth in just 8 minutes. When X-rays hit Earth's upper atmosphere, they ionize the D layer of the ionosphere. This sudden ionization absorbs high-frequency radio waves instead of reflecting them back down, causing sudden ionospheric disturbances, or radio blackouts, on the sunlit side of Earth. However, solar flares alone do not physically fry power grids on the ground. Power grid disruptions come from coronal mass ejections, massive clouds of plasma that take 1 to 3 days to reach Earth and induce ground currents. It is such a crucial distinction. Flares affect radio communications almost instantaneously, while CMEs trigger physical geomagnetic storms hours or days later. Moving to our third article, photographing satellites and Starlink trains, we step into the shoes of night sky photographers. If you've spent any time looking up at the night sky recently, you've likely noticed long strings of bright, artificial lights drifting in a straight line. These are newly launched satellite constellations, like SpaceX's Starlink, moving through low Earth orbit. The article breaks down the optical physics behind satellite visibility. Satellites don't emit their own light, they act like giant mirrors reflecting sunlight. This is why they are most visible during astronomical twilight, shortly after sunset or right before sunrise, when the ground observer is in darkness, but the satellite at an altitude of 400 to 550 kilometers is still illuminated by the sun over the horizon. For astrophotographers, capturing these streaks requires precise planning, understanding target orbital inclinations, and managing long exposure settings without oversaturating background stars. Next up, we have how solar flares impact modern electronics, which looks closely at the engineering vulnerabilities of our interconnected technology. As we progress through solar cycle 25, solar activity remains elevated, bringing heightened risks of single-event upsets in satellite electronics. When energetic solar particles hit microprocessors in orbit, they can flip bits in binary memory, turning a 0 into a 1, which causes software glitches or commands guidance computers to reset. On the ground, long-distance power distribution lines act like giant antennas for geomagnetically induced currents. Power grid operators must proactively manage transformer loads during G3 to G5 level storms to prevent hardware overheating. And finally, our fifth article explores planetary science, the discovery of asteroid moons and their celestial systems. For a long time, astronomers assumed asteroids were solitary rocks floating through space. Today, we know that a significant percentage of near-Earth objects are actually binary or triple systems, where a main asteroid is orbited by one or more smaller moons. How do these tiny moons form? Often through rotational fission. When solar radiation pressure, known as the YORP effect, gradually speeds up an asymmetrical asteroid's spin, centrifugal forces cause loose material to spin off and assemble into a moonlet. Studying these binary systems is invaluable for planetary defense because deflecting a double asteroid requires entirely different kinetic strategies than nudging a single, solid mass. Let's turn our attention now to recent space events and tracking alerts across our network. We start with a fascinating statistical flag, an active historical anomaly alert on the KP index. Our automated monitoring detected that recent geomagnetic spikes reached KP 5.7, which is 2.0 for standard deviations above the 30-day baseline mean of 2.9. It is important to understand what a statistical anomaly means in space weather analysis. It doesn't automatically mean a catastrophic physical event is occurring, rather, it indicates that current conditions are deviating significantly from the monthly statistical norm. It signals an underlying change in solar output, in this case, the transition from quiet background wind to high-speed stream impact. Next, we have two remarkable severe forecast divergence alerts. This is where human space weather forecasters and artificial intelligence modeling systems strongly disagree on upcoming trends. The first divergence is on the rapid solar wind acceleration. Human expert consensus places the likelihood of rapid wind acceleration at 75%, while AI consensus sits at just 35%. That is a massive 40 percentage point disagreement, resulting in a high divergence score of 78 out of 100. The second divergence alert asks, will a CME trigger a G2 or greater geomagnetic storm in the next 14 days? Here, human consensus stands at 90%, whereas AI models estimate only 52%. Why are human experts so much more confident in elevated activity than machine learning algorithms right now? Human forecasters heavily weigh complex magnetic shear patterns in active regions on the Sun's visible disk, drawing on historical intuition, while AI models adhere strictly to historical statistical training weights. Tracking who wins out in these divergence events helps us refine both human analysis and machine learning predictive capabilities. Looking ahead on the celestial calendar, we also have 2 minor meteor shower watches active. The Draconids meteor shower will peak on October 9th, originating from parent comet 21P Giacobini-Zinner, with its radiant in the constellation Draco. Following that, the Taurids meteor shower peaks on November 5th, driven by orbital dust from comet 2P Elench. The Taurids are known for low hourly rates of around 10 meteors per hour, but they frequently produce slow-moving, intensely bright fireballs that make for incredible viewing under dark skies. Now, let's step into our fact-check segment, where we sort verified astronomical facts from widespread rumors, viral claims, and misunderstandings. First claim under review: are there aliens living on Earth? Our rating on this claim is unverifiable. Here is why: neither NASA, the All-Domain Anomaly Resolution Office, AARO, nor any independent scientific institution has presented empirical, peer-reviewed proof of extraterrestrial entities residing on Earth. However, scientifically speaking, absence of verified evidence is not absolute proof of absence. Reports like NASA's 2023 UAP independent study acknowledge that a tiny fraction of atmospheric observations remain unexplained due to data limitations. Because rigorous science demands positive verification to prove or disprove a universal negative, classifying this claim as unverifiable is the most intellectually honest verdict. Second claim: was the first ever moon landing, Apollo 11, a hoax? Verdict: false. The Apollo 11 moon landing on July 20, 1969, is one of the most thoroughly documented historical events in human history. It was independently tracked by radio observatories around the globe, including by the Soviet Union, who had every political reason to call out a fake if one existed. Furthermore, the 382 kilograms of lunar rock samples brought back hold unique micro-impact craters and isotopic ratios impossible to manufacture on Earth. Plus, retroreflector mirrors left behind by Neil Armstrong and Buzz Aldrin are still used today by ground lasers to measure the precise distance to the moon. Third claim: are there aliens anywhere in the universe? Verdict: unverifiable. While astrobiologists calculate high statistical probabilities for microbial or intelligent life given the hundreds of billions of stars in our galaxy, we currently lack definitive, reproducible spectroscopic or physical signal detections. Fourth claim: are there any current or planned human bases on the surface of the moon? Verdict: partly true. Why partly true? Because no human base currently exists on the lunar surface today, all Apollo stays were temporary exploration visits. However, that planned a part of the claim is fully accurate. NASA's Artemis program, alongside international partners like ESA and JAXA, has formally documented architectural roadmaps to construct sustained surface habitats near the lunar South Pole. Fifth claim: SpaceX has already established a human colony on Mars with over 1,000 inhabitants. Verdict: false. No human has ever traveled to Mars. While SpaceX CEO Elon Musk frequently outlines long-term strategic ambitions for a future Martian city, zero uncrewed or crewed Starship landings have occurred on Mars to date. Time for today's daily brief, where we focus on our headline astronomical story, the close flyby of Asteroid 2026 PX alongside our recent geomagnetic activity. Asteroid 2026 PX is a near-Earth object currently sweeping through our celestial neighborhood. Orbital tracking data from NASA's Center for Near-Earth Object Studies confirms that this space rock is making a completely safe passage with zero risk of Earth impact. What makes today so interesting is how this flyby coincided with the G1 geomagnetic storm we discussed earlier. As 2026 PX cruised past, a high-speed solar wind stream pushed solar wind speeds up to 544 km per second. The interplanetary magnetic field Z component, known as the BZ, held steady near 3.3 nanoteslas, allowing efficient particle coupling with Earth's upper atmosphere. This event pushed auroral oval coverage up to roughly 26%, providing sky watchers at high latitudes with impressive light shows. At the same time, lingering debris from Comet 109P Swift-Tuttle, the source of the Perseid meteor shower, continues to cross Earth's orbital path through August 24. Even though the peak of the Perseids passed on August 13, dedicated observers in dark sky locations are still catching sporadic meteors streaking across the night sky. Looking at the 72-hour outlook, solar wind speeds are expected to gradually decline as the coronal hole stream rotates away from Earth's direct line of sight. The KP index should return to nominal, background levels between 1 and 2 over the next day or two, bringing quiet space weather conditions back to our orbital environment. Before we wrap up today's show, here are a few quick reminders to help you stay ahead of the next solar storm. Head over to flain.com for live space weather data, real-time KP index updates, aurora forecasts, and interactive orbital dashboards. It is the official website of Flyby and the best place to see what the sun is doing right now. Be sure to subscribe to the podcast on your favorite audio platform so you never miss a daily space weather update. You can visit flain.com/podcast to browse all our previous episodes, transcriptions, and comprehensive show notes. Follow Flyby across social media for real-time space weather alerts whenever solar flares erupt or CMEs are launched toward Earth. Join our vibrant Flyby community to share aurora photography, discuss orbital tracking, and connect with fellow space enthusiasts. And don't forget to download the Flyby app to get instant push notifications delivered directly to your device the moment geomagnetic storm conditions reach alert levels. Thank you so much for joining me today on the Daily Space Podcast by Flyby. Keep looking up, stay curious, and I will catch you again tomorrow.